Our last speaker is Dava Newman, former Deputy Administrator of NASA. As of the 20th of January 2017, Dava resigned from a position at NASA and is now back at MIT as the Apollo Program Professor of Astronautics. Dava, the stage is yours.
Hello, everyone. It's a real pleasure to be with you. And I look forward to taking you, continuing in the spirit of David's talk, exploring from Earth to Mars and outer space. So let's get started. We have fundamental questions. The three enduring questions that we ask about exploration are we alone on this planet Earth? Are there other habitable planets? And is there life in the solar system or other solar systems? The evidence is mounting. So this is a beautiful image from the Hubble Space Telescope. It's been searching and discovering for the last 26 years. So I know we have some folks under 26 in the audience. So your entire lifetime, our great Hubble Space Telescope has been trying to prove kind of the solar system universe. You know, again, are we alone? Are there other habitable planets? And evidence is mounting. I think we will become interplanetary species. That's really exciting and kind of inspires all of us to keep doing what we do every day. Now, Professor Hastings said Pluto was no longer a planet. Pluto has a heart, and Pluto is a dwarf planet, I might add. So I still count Pluto, and it was pretty amazing to get there just 2 years ago. 30 years of people's careers and life, and it took 9 years just for the mission to arrive at Pluto. It's revealing the secrets of Pluto today. Has one of the most interesting moons we've ever seen because it's almost the size of Pluto itself, and now we know what the constituents, what's it's made out of. You know, ice. It's kind of an icy planet, if you will. Dawn. If you haven't heard of the Dawn spacecraft, it has ion propulsion. David just mentioned ion propulsion. We are going through the solar system with advanced propulsion and technologies. So on Dawn, the spacecraft is now at another dwarf planet called Ceres. And has those two little twinkling eyes. We were looking at those. We didn't know what they were. And when we zoomed in and we got closer in the orbit around Ceres, look at the chemical constituents. That's sodium carbonates. You should be saying, that's fantastic, because when we search for life in the universe and you find sodium carbonates, you are really excited, because these are some of the characteristic signatures. And then we zoomed in even closer, and we found Ahuna Mons. Move over Mount Everest, because Ahuna Mons is 5 kilometers high and 20 kilometers wide. Quite an interesting, geographical find. So that's what we do in our exploring. And hopefully you know that we're at Jupiter today with Juno, the goddess of Jupiter, the mission that's now in orbit around Jupiter. And that is really one hairy orbit. It's a polar orbit. Jupiter is really extreme. The radiation environment in Jupiter is 20 million times more severe than here on Earth. So that's hard to design a spacecraft that can withstand, and all of our instruments that can withstand this. We zoom in around the polar orbit and we zoom right back out. The instruments are all working today. We're revealing, again, the secrets and mysteries of this gaseous planet. On the bottom right, this is when we call all citizens of Earth, all of humanity, say, come join us on our missions. And we have something called JunoCam on the Juno mission, and that's for all of us. And we ask the world, we say, where do you want to look at Jupiter? And that's a little camera called JunoCam, and we point it, and we take pictures of wherever people all over the world want us to take pictures of, and we share that with the world. Again, in the nature of open science and open data, to make sure that everyone can come explore on any mission they want to. This is another recent launch. We just launched this in September. It's called OSIRIS-REx, and working very well today. It's going to an asteroid. It's the first mission that will go to an asteroid, land, take a sample, and in 7 years, we get it back on Earth. And we'll see what those constituents look like. We're pursuing over 100 scientific missions today, so it's really exciting. Showed you images from Hubble. But the next great observatory is the James Webb Space Telescope. Webb is built and designed. Those are 18 articulating mirrors, really incredible systems behind it. And we're going through thermal vacuum chamber testing now. It's in our NASA Goddard Space Flight Center in Maryland. Goes to Houston for final vibration thermal vac chamber testing. Goes to California. The main contractor is Grumman. And after it's tested, it gets on a boat, goes down to French Guiana, and it will launch on an Ariane 5 in 2018. Everything's on schedule and performing very well. Okay, back up one. Just wanted to give a shout out to take you even further into the universe, if you will. As of today, we have 6,000 exoplanets. Are we alone? Are there other habitable worlds out there? Well, the science of exoplanets didn't even exist 2 decades ago, but it exists today, and that's where some of the best scientists in the world are flocking to because it's so exciting. These are artistic views of exoplanets because, of course, we've never seen one, but we know that they're there. And a shout out to JPL and some of our artistic friends, trying to help us vision what could they be? What do they look like? The first one was 51 Peg B, discovered. And Kepler 16b is one of my favorite exoplanets because it's a true binary system. 2 suns, so you get a double shadow. Luke Skywalker and Tatooine was science fiction, now proven in this incredible. So again, 6,000 exoplanets today. We've put up 1,200 of them are in a catalog. But there's 24 of them that are really exciting. Why? Because we call them, they're in the Goldilocks zone. Not too hot, not too cold, could just be perfect for life. So they're very, very exciting, and the exoplanet work continues as well. Okay, I want to get a little closer to home now. We'll get to Mars, and David shared the incredible, exciting work for our Mars Science Lab opportunity. But I want to show you the last 50 years of successful Mars exploration in this video.
Preliminary analysis of this data. Can you describe what you see on Mars?
Yes, it's there.
Right now, the wheels of curiosity have begun to blaze the trail for human footprints on Mars.
I just wanted to call and say congratulations to the entire Mars Science Laboratory team and really all of JPL. You guys should be remarkably proud.
So that's what I spend every day thinking about, is how do we get humans to Mars in the 2030s. And again, all those successes. So we have been exploring Mars for quite some time with a lot of successes. And there is a plan, a long-term plan, We're currently in phase 1. It's a 3-phase plan. We're in phase 1, and that's close to Earth. That's on the International Space Station. Tell you a little bit more about what's happening there in terms of research. And then we move out to what we call the proving ground. That's Earth-Moon orbit. That's where we really have to buy down the technologies. We have to invest in technologies, understand them, before we can get to third and final phase, which is Mars orbit, and then eventually sending humans to Mars. Let me tell you a little bit about recent data coming back from Mars, from our rovers and precursors. The missions to Mars, the robotic missions, continue the entire time through the 2020s and the 2030s. So we have found the evidence of water on Mars. That's a big deal. We're searching for life. We knew there was ice on the north and south poles of Mars, but just recently we have flowing water. Now, it's very high in salinity. It has high percolates, so you're not going to drink it. It would kill you. But it's still a huge find because we say when you're searching for life, follow the water. If you can turn down the volume on this one, thank you. So this is really important as well. We now know why Mars lost its atmosphere. Earth and Mars, both 4.5 billion years old. Sister planets. That's why we're so interested in Mars. Mars probably was wet, warm, and wonderful. It had life. We think about 3.5 billion years ago. At least that's the hypothesis. Earth today has a global magnetic shield. Lucky for us. Life's worked out pretty well on Earth. For Mars, not so lucky. Mars has no global magnetic shield, and today is left with 1% carbon dioxide atmosphere. So what you see in this animation from our MAVEN observer at Mars is literally the solar wind and radiation ablating the ions away from Mars' atmosphere. Ionization, the ablation of the ions away from the Mars atmosphere to leave it today with just 1% carbon dioxide atmosphere. So, phase 1 of the journey to Mars is, as I said, on International Space Station for 16 years. It was great to talk to the students yesterday at Art Science Museum, and most of them were 16 years and younger. So you just have to stop and, reflect. Anyone 16 years and younger, they've never known a day of their life without humans living 24/7 off the planet, living in our International Space Station. It's pretty remarkable. We have 6-month increment missions for each of the astronauts, 6 people at a time from all over the world, and 5 main partners, NASA, Russia, Japan, European Space Agency, and Canada. But we've had 95 nations send up experiments. Each 6-month increment, our astronauts, they do about 250 experiments. So we're doing world-class science up there. We're also looking at technologies. But I asked Scott Kelly, who you might know from his 1-year mission, what are some of the technologies we really need to work on right now, right on space station, to help humans get to Mars? And this is what he said to me.
I think the life support systems that we need to keep us alive in space are ideal candidates for demonstrations for our future journey to Mars, as well as space suits. We need, I think, new spacesuit technology that requires less maintenance in space, and something that's going to be easier to work in on the surface under the Martian gravity.
So he might know that I have a background in spacesuit research, but a funny true story is that while he was up on space station, he actually called down to my office at NASA, and I was in a meeting, because, you're always in meetings, right? And it just looks like a call from Houston, Texas, because it has a 713 area code. So I said, oh, I can call them back in Houston, let's finish our meeting, right? And then I got my message. There was Scott Kelly from the space station. Dave, I wanted to tell you about the EVA we just did. That's extra vehicle activity. So what I learned was, not to ignore calls from Houston. So, because you just can't call back up space station and say, oh, sorry, I missed your call. He called back, thank goodness, 30 minutes later, and I got to talk to him. And so it was a big deal. It was a big deal for us to have a 1-year mission. Again, we have typically 6-month increments, but we're getting ready for Mars. Mars is a 3.5-year mission, and we're going to go out in about 8 months, take about 1.5 years to get home, and we're going to be on the surface of Mars for 500 or 600 days searching for life. So will our astronauts be able to handle that? What about their muscles and bone? We have a serious musculoskeletal deterioration. What about the radiation environment? Probably the #1 issue. What about psychology, right? how are we going to keep these folks, 4 to 6 people, from killing themselves, right? You're locked in something that's a very small, isolated, confined environment. So these are all the things that we research and study, and we're going to have longer missions and continue with some of our one-year missions. Here's Scott and astronaut Shell Lundgren eating vegetables. Now, you can't see this, but it's our third. This is another life support. And how do you keep people healthy and well? So we're growing some of our own food. Really important first step. And with their Japanese colleague here, nothing like a fresh salad up on space station when basically you're eating camping food. And here are some of my top technologies that we really need to. We're going to be on space station until 2024. All the partners agree on that. And these are just some of my favorite technologies to show you what we're investing in, what we're looking at, in terms of different technologies, inflatable habitat structures. We have an expandable right now on space station, the Bigelow expandable, really great partnership, with private industry in space manufacturing. Fire is just incredibly interesting, not advised in space, but incredibly interesting because of the physics and how things burn, humans and robotics and a lot of the technologies. I wanted to also make sure to build on David's point as well. And I call it the new NASA in terms of the public-private partnerships are unprecedented. It goes with our innovation strategy in terms of what can we do and how can we invest in private industry and some new folks to really bring down costs, to be more efficient. And it really is important. This is for cargo now to space stations. So SpaceX is going to, they just had a recent accident. They're going to get back up at it. Actually give an award for failure at NASA. Something we have to learn to do. You don't want to fail, but guess what? We have to get comfortable with it. If you're going to make higher risk bets, you're going to, have some things. So cargo now is being delivered, not by NASA, but we're paying for services. We're paying SpaceX and Orbital ATK, and soon to come on board is Sierra Nevada. And with sending our astronauts to space station, Boeing and SpaceX have those contracts. So it's a new way to think about how space is for everyone, and also from the government, from the U.S. government perspective, how to invest in the economy and the private sector. Also, the Russians and the Japanese are delivering cargo to space station, and the Russians right now are the only folks delivering astronauts. I'll show you our next big rocket. This is how we get to the moon and beyond. So that's the Space Launch System, designed, built, investing in over 1,000 companies. The first mission is Exploration Mission 1, will launch in 2018. without astronauts, and then in the early 2020s will be the first mission, cislunar space, Earth, Moon, orbit, and then to deep space, and that'll be early 2020s, and we keep flying the entire decade of the 2020s. So it's the world's next heavy lift launch, and hopefully there'll be even more capability, but this one is well on its way. So to kind of show you, again, it's about the people. All of our exploring and spaceflight is about everyone being so passionate, and making these, turning these dreams into reality. So, truth in advertising. It's not an eye chart, it's an infographic about all of the missions to Mars so far in human history from the 1960s. I only showed you the successful ones in my video. It's hard. It's really far away. Red, Soviet Union early missions, blue, US, NASA missions. And the point here is that there's a lot of green check marks in the last decade or two, and that's what we're counting on. We're counting on the success, and everyone is involved. Right now, the Indian Space Agency has an MOM, the Mars Observer mission, and then what a great success for the Indian Space Agency, and we work with them, give them our deep space network and the navigation, and most recently the Europeans have the ExoMars, successful orbiter. The lander didn't fare well. That's okay. That's a technology demonstrator. It's really hard to land on Mars, as David said, but we're all in this together, and now the world has really had unprecedented success. So we're sharing all those lessons learned, because anyone's success is all of our success. That's how we look at it. Here's some of the technologies. We can't just go to Mars tomorrow, especially with humans. Why not? Well, these are some of the technologies we really need to work on. Both in David and my videos, you see the capsule coming in hot. That's entry, descent, and landing. Right now, we know how to do that for about 1 metric ton. Okay, maybe 2 metric tons if we push it. We've tried to land on Mars every which way. Airbags, retro rockets, cranes, you name it. For the first human mission, 10 to 20 metric tons. We don't know how to do that. We have to figure out the entry, descent, and landing. It's hard. We're teaming up, again, with industry. We're working that one really hard. Then, once we successfully land, we also need an Ascent Vehicle, because it's a round-trip mission with our humans. So you can take a look. In situ resource development. We have to learn how to live off the land. Literally all successful human exploration in history has learned how to utilize the land and resources. We can't bring everything with us. The 3D printing has to happen on the Martian surface. I give the challenge to students, you have to make the maker. You don't get to bring your maker with you. You get to make that maker on the surface of Mars, have it make itself, and then produce some of the infrastructure that we need. Big challenges, but exciting. So I want to close with some slides back down to my favorite planet, if I didn't say it, is Spaceship Earth. Mars is number 2 in my book. And this is a picture from our Discover mission. It's at Lagrangian point 1. That's halfway in between Earth and Sun. What it's doing is a big space weather buoy. It's looking at the solar radiation, solar wind, and saying, hey, Earth, 1.6 million kilometers away, here's what's coming your way. And really important for a lot of the things we've been talking about today, for our communications, for our satellites, things like that. And it's just the most beautiful picture, again, to remind us that we're all on this planet together. Call it Spaceship Earth, and it's the only one we have. We have 20 Earth-observing satellites today, and that orbital view, that perspective, is really, really important. I think kind of getting off the planet, the orbital view. And the data that's coming back in Earth Sciences is about sea temperature, sea rise, soil moisture mapping, the ice melt in Greenland and Antarctica and over the entire world, giving us a lot of data. I want to show you the world's, the recorded temperature data for the last 140 years. You can raise your hand when you're born if you want audience participation time, since we're getting to the end of the afternoon. So from 1880 to 1884, here's the world temperature. Blue is minus 1 or 2 degrees C below the average, and yellow and orange are 1 to 2 degrees Celsius above the average. Thank you for participating. It's hot. It's getting really hot. Broke the record in 2014 for our hottest year on record. We broke the record in 2015 for the hottest year on record. We just have the cumulative 2016 data, and we just broke all-time records. Matter of fact, 12 of the last 13 months, we've just broken the records for temperature. So that's the data, and I think it's urgent. We need to do something about it. So I end with a message on what I call STEAMed instead of STEM. I've dedicated my whole career to science, technology, engineering, math, and about the next generation. But I'm changing the conversation now, very intentionally. I always bring in the arts, the artists, the historians, the journalists. They paint our pictures. Only folks I know who can paint my pictures about how humanity is going to get to Mars and what it's going to look like. But I've put a D on the end now, too, for all the 3D makers, because we have a new generation of 3D makers, and if they don't see themselves as a scientist or even as an aerospace engineer, that's okay. The conversation needs to be inclusive and tell everyone this is for you. No more weeding people out. I know when I got to engineering school, everyone was really proud that only, 20% of the folks were going to make it and kind of weed you out. But I think that's the wrong message. I think the message has to be very inclusive and say, what do you want to do? You want clean water, clean energy, then you're in. And we as faculty members, as teachers, as professors, it's our job to make sure that those folks succeed. So to me, it's a message of STEAMed, and I'm pretty steamed, actually. We're not making progress sooner and more quickly, so I like the meeting. So again, leave you with this image of the beautiful Earth, and realize how precious it is. If we shrink Earth down to the size of a basketball, our life support system, kind of what separates us from the rest, is 3 human hairs thick. So I think that's good perspective to leave you with. And thanks for your attention. And now I think we're going to turn it over to the panel.